Hi, everybody, and welcome to my talk today on multi-stage chemical production scheduling under uncertainty with deep reinforcement learning. My name is Christian Hubbs, and my co-authors on this were Drs. Adam Kellaway, Nicholas Sahanidis, Ignacio Grossman, and John Wasik, without whom this would not be possible. So today I'm going to be talking about planning and scheduling for our chemical production processes at Dow Chemical. So we oftentimes use these terms interchangeably, but they are absolutely critical for our decision-making process, ensuring that customers get the products that they request in a timely fashion while managing our manufacturing sites to ensure inventory levels are respected and sourcing is properly accounted for. This works across multiple different scales for planning for different plant sites, business, or even geographical region, as it may be. With most of our plants, they are multi-product plants, so they can make product A, B, C, D, and so forth. The production planning process is very difficult. It's stochastic. We have humans that actually wind up doing this. There's a whole lot of sources of uncertainty, from demand uncertainty, price uncertainty, to product availability and maintenance issues that may arise and derail a perfectly good schedule. Suddenly something goes down. It doesn't work in the plant, and now you have to scramble, reschedule, contact your customers, tell them that there's going to be a delay, communicate with account managers, and so forth, in order to try to mitigate anything that might occur in those types of situations. So we've tried to develop optimization tools and other things in the past, but we wind up still relying on humans in the loop who actually do the work using tools such as Microsoft Excel, Lovely, and Legility, as you can see a screenshot of here, which is a planning tool that we use widely across the company in order to help planners and schedules assist them in making their schedules. So because a lot of the tools that we haven't are really there just to assist and support, and it's still a very manual process, we were thinking we want to take another approach at this to try to improve our scheduling and decision making in this key role. And to that, we turn to reinforcement learning, which has had a wide success in game playing applications in very complex scenarios and situations. And so we think, hey, we could maybe try to use this to deal with a lot of the scheduling problems that we have, especially because it is something that's very well adapted for doing things under uncertainty. In short, reinforcement learning is training an agent using a feedback as a reward signal in order to learn a good policy that will map states to actions. A state is basically all the relevant information that you need in order to make a decision, and your action is that decision. And that reward is going to be whatever that feedback signal is going to look like. You want to try to maximize your reward or your objective. In this case, we want to try to maximize our profitability as a company, and it's going to take a number of different inputs, and we try to train this agent in order to do so as effectively and efficiently as possible. So one of the issues with machine learning in general and reinforcement learning in particular is that it requires a lot of data. And we at Dow do not have all the data in the world, even though it's a very old company. A lot of the plants and systems, products, etc. that we have are fairly modern. They might have data only going back 5 or 10 years. Now it's hundreds of years that we might need to actually properly train the system. So we have to actually build a simulation. To this end, we collected a massive amount of data at Dow in order to parameterize a number of different demand models and pricing models and other things, so we can actually effectively run a simulation of our Dow plants. Then we can plug the reinforcement learning agent into the simulation so that it can start to make decisions and get feedback based on the simulated parameters. And we do that in order to try to maximize its on-time delivery scores, minimize its inventory, minimize off-grade, and enforce a few different constraints such as campaign lengths and illegal transitions to make sure that those constraints are not violated. In order to do that, we wind up using something called action masking. So this is a technique whereby we essentially make certain actions, give certain actions a 0 probability chance of being selected. So when you do a forward pass through these, through a deep neural network, that's going to be your reinforcement learning agent, you get a action distribution or a probability distribution over the actions available to you. And by masking it, we essentially provide a negative infinity on those different actions, then pass it through a softmax again so they effectively become zero. This has the effect of enforcing these constraints so that these actions are never selected that would violate, say, a transition, so that would never be an illegal transition, or it would never make too little of a product, so that it respects its minimum campaign lengths. This helps to reduce the search space so that it can learn better policies faster and hold to those constraints, where otherwise you'd have to do reward shaping or other things along those lines in order to try to incentivize the system to not make those bad decisions. So we found this to be very effective and useful for us as we try to train this to maximize its profit and balance the inventory costs, off-grade costs, and its customer service level that it needs to achieve in order to perform well. So what we're doing, this is a multi-stage system. We are training the RL system to schedule the reactor stage, which is a continuous reactor that we have. And then we have a greedy heuristic that is actually doing the scheduling on the bagging line, so in the second stage. So we have 5 different products that can be produced, and each of those can be packaged in 3 different ways to be shipped to different locations, etc. And the bagging line will handle that for us, while the RL agent will do the reactor scheduling. The other thing that we used was population-based training. So this is similar to a genetic algorithm approach, whereby we are able to parallelize a lot of our RL agents, create a number of different policies with various hyperparameters. They can start training in parallel. And then as we start to get different experience, the algorithm will begin to prune certain agents, and it will choose certain agents that will be mutated together to change different hyperparameters. And then if an agent is below the cutoff level and is going to be pruned, it will be replicated with a good policy. So we might have 2 versions of the same policy operating simultaneously, so that we can explore those good policies further and try to get better information that can then inform future policies and future agents as we try to search as effectively as possible. And this winds up taking advantage of that parallelization that is available through reinforcement learning, because we're essentially doing a lot of Monte Carlo simulations, which are independent of one another, but then we can use that data to make our updates. And so it's much faster than sequential decision making, where you maybe set your hyperparameters, run through and train for a few hundred episodes or iterations, whatever it might be, a system, and then you look at it, change the hyperparameters, and do it again and again, or a different type of grid search type approach where you parallelize, but you're sort of just randomly checking different hyperparameters. We try to be a little bit more intelligent with the population-based training, and we found good results from that. So looking at our results, you can see here on the left one of the agents that we selected. Over time, it's able to learn a good policy in order to ensure good product availability, and at the same time, as the product availability is improving, and this is a proxy for our customer service level for our schedulers, the costs are able to go down. So it's able to make better decisions to get the products delivered to our customers on time while keeping costs low. So what's not to like about that? Before we actually go and deploy it, though, we do want to check it against some historical data. So we have a holdout set of just historical data shown in orange here, and about 1,000 simulated years in blue. Each dot represents 1 year. And this historical data, because we only have about 5 or 6 years of data, what we wind up doing is we do a walk forward type of approach, where we take a 52-week slice, and that is 1 year. We advance it 1 week with another 52-week slice, and that's another year, and so forth, to try to give us a better, to try to make the most of our data, basically, because we do have a limited amount in this holdout set. So once we validate it against our trained agent, and we take a look and say, hey, okay, this looks like it's still performing fairly well, even if the data does differ a little bit from its training data, So we're comfortable enough with it, with its performance in order to roll this out and actually see how it performs in practice. So we get to deploy our system and seeing really how this RL agent performs in the wild. So we basically, if you look at this diagram on the right, we've covered that top part where we train it in simulation, and we make all of our decisions, pass all of our data in our state, get our reward back through our simulation. And now we're focusing on that bottom section where we actually make our decisions and we pass it through a human scheduler who's going to approve it or make some slight tweaks. We take that data, that input, and then we pass it to our ERP system that is going to actually implement it in the real world. And we take that data and repeat on a daily basis. This has been very helpful for us because we have been able to ensure that somebody who has some experience scheduling this particular plant is able to give us feedback. Hey, maybe we missed a constraint, maybe we need to take some additional data into account, what have you, or the algorithm's just behaving oddly, and we're able to go troubleshoot that by having them in the loop, but also able to build some confidence in the schedules that are actually being produced and make sure that we don't have anything that goes off the rails. So this has been very helpful and given us a lot of good feedback over time. We also have other metrics that we've been looking at. One of the things that we've been using quite extensively is our principal component analysis, so PCA. And you can see this in the first plot on the left where we have the first and second principal components of our states plotted here. So in the blue, we have the states, the training states, and in the orange, we have all the actual states that the system has seen since it had been implemented. So this is about 5 months of data when the snapshot was taken. And what you can see is that this star on the orange star gives basically the real data center of PCA space versus the blue star where it has been trained. Why this is important is because we find, as shown in B, that there is a negative correlation with the distance from the training data versus where the states are actually being executed. So when you are very close to your training data, as we would expect, or the center of your training data, I should say, the rewards tend to be higher. And this makes sense because the algorithm has seen similar situations in the past. It has a lot of data based on that, and it's able to make good, high quality decisions. When it starts to drift away from that, then that performance starts to decay as well. In the far right, plot C, we see how this is actually performed over time in production, where we have each one of these individual state decisions plotted with the reward that the system received, as well as being color-coded by the distance in PCA space. So you see it starts off pretty well, performing near the top of its range. Then it drops down around day 40, oscillates a bit. About day 70, it shoots up again, and then it drops down again. And then as you see around day 90 to 100, the PCA space, that PCA distance starts to really increase. So the first drop off from day 40 to 70 or so was due to a lot of production issues. So had a really bad month in the plant where it shut down for unplanned reasons, maintenance issues. Started up again, shut down, started up, and then finally, we got all the bugs worked out of the physical plant, and so it was able to produce again. So inventory levels were very low. As you can see, the distance started to increase, not dramatically in PCA space here, but it did start to move, and rewards were significantly lower because it wasn't producing on a daily basis as it should. But what you can see then later, in that second part where it dropped down around day 90 or so, this occurred when we were introducing a new data layer into our ERP system. So this was something that actually happened upstream from our ingestion points and wound up causing a number of different issues. For example, inventory was being double counted as they were trying to make this system upgrade. And so what we saw was that our AI system wasn't performing very well because it was seeing far too much inventory for certain products and not enough demand. So it was making decisions based on that. And so one thing that's very nice about looking at this PCA plot is that we're able to see actually how these states start to drift away. And if they get out of whack like this, we're able to realize, hey, something's probably not right here. It's a red flag. It's an alert for us to be able to go to those teams that are maybe upstream of us and say, hey, look, there's something wrong with the data that we're seeing that's coming in. So this is a really good way for us to feedback and improve our data governance and controls as a company by using these types of algorithms and approaches as a side effect for the main goals that we're trying to get. So the results so far have been promising. It's been in production now for about 6 months. It helps to reduce the decision time and the cognitive load on the planners, which helps to reduce their stress. And it helps to free up a lot of the time for the schedulers to do more work with customers, improvement projects, and other things like that. And this is a high stress job, so it does tend to have quite a bit of turnover. And so this is something that we found to be very helpful for new planners as they're able to come online and see how the system might be able to schedule. That has been trained on a few thousand years of DAO data or simulated DAO data. So it's the most experienced planner that we have in the company. And so it's able to help support the decisions of the inexperienced and new planners as they come online. So the state PCA approach that we have has been very helpful for us to diagnose the performance of the model, to see when something might be amiss, and so we can go back and fix that and work out a lot of those data issues that we have. 2020 has been a bit weird from our demand perspective. I don't need to explain the oddness of 2020 to anybody. So the fact that the PCA space is off a little bit, we're not overly concerned about, because it has been an outlier as far as a year is concerned. We're expecting to see that to move back towards our simulation center as we move forward. If not, we're just going to update our models and try to improve the accuracy on that front. But even with that difference, we're still seeing good results out of the model so far. So our next steps are to be able to use a multi-agent RL approach to do scheduling for all stages and incorporate other realistic issues such as planned downtime for turnarounds and other things into the system so that it can schedule over those, because currently we have left that out. And then be able to expand the model so that we can optimize a full site and then multiple sites simultaneously to really optimize our network. So that's an overview of the research that we've been working on, and we will take your questions now. Thank you.